Everyone watched the series. Millions of us tracked every bolt, every heartbreak, and every triumph as Matt Armstrong brought a totaled Bugatti back from the dead. It is, without question, the most ambitious, independent automotive project of our generation. But here's the thing about high-level engineering. It's unforgiving. While the world cheered for the engine firing up, a group of engineers and fabricators were watching one specific detail, holding their breath. It's a decision that Bob, a brilliant welder, and Matt made together. They chose to repair a critical bracket rather than replace it with a CNC machined part. On the surface, it looks like a victory, but beneath the surface, there is a physical risk that nobody in the comments is talking about. A risk that doesn't show up at idle. It only reveals itself when the W16 is pushed to its absolute limit on an open road. If that risk becomes reality, the result won't just be a breakdown, it could be catastrophic. To understand why this is such a big deal, you have to look at the environment. Matt is working without factory support, without the proprietary CAD files, and without the diagnostic software that keeps these cars running. He's essentially reverse engineering the most complex internal combustion engine in the world. When you're in that position, you're forced to make thousands of micro decisions, often under immense pressure from a global audience waiting for the next update. Matt and his team have performed miracles, proving that the right to repair movement isn't just a political slogan, it's a reality. But in the rush to solve a problem, there is a thin line between a smart repair and a risky compromise. Today, we're looking at that line. Let's talk about the component in question, the bracket holding the crank position sensors. In a standard engine, a sensor bracket is mundane. In a W16, it is the heartbeat of the timing system. These three sensors are the only things telling the ECU exactly where each piston is in its 16-cylinder cycle. If these sensors are misaligned by even a fraction of a millimeter, the ignition timing is thrown off, the fuel mapping fails, and the engine either misfires or refuses to run entirely. Matt's fear was that a 3D scan followed by a CNC machined replacement would lead to that exact misalignment. It's a logical, cautious argument. But while he was focusing on the risk of misalignment, he ignored a much more dangerous structural risk inherent in the repair he chose instead. This is where we need to get into the metallurgy. When you weld a crack in a high-performance casting, you are creating a metallurgical nightmare. Think of the original bracket as a precisely engineered crystal structure, poured and cooled in a factory-controlled vacuum. It's uniform. When Bob, as talented as he is, takes his TIG welder to that piece, he is introducing extreme, localized heat. The metal melts, then it cools rapidly in ambient air. This creates what engineers call the heat-affected zone, or haze. This is the area surrounding the weld that wasn't melted but was heated enough to change its internal structure. The haze is weaker than the original casting. It's brittle, it's inconsistent, it's a borderland where the metal has forgotten how to be strong. I see the comments. Bob's welds are cleaner than Bugatti's factory work, or he added infills, it's reinforced. And I agree, visually it is a piece of art. Bob is an elite craftsman, but physics doesn't care about beauty. You can add all the reinforcement you want, but you cannot eliminate the heat-affected zone. When you introduce a weld into a high-load, vibration-heavy environment, you are essentially introducing a stress riser. You've created a place where the material is different, where it expands and contracts at a different rate than the surrounding metal. The more you reinforce it, the more you change the thermal profile of the part. You aren't fixing the metal, you're just masking the inconsistency. Here is the tragedy of the situation. Matt's concern about sensor positioning was actually completely solvable. CNC manufacturing isn't a guess-and-check game. It's a process of verification. You machine a prototype, you measure it with CMM equipment, you verify the sensor holes against your 3D scan data, and you adjust the tool path. You do this 10 times if you have to before you ever mount the part. By choosing the repair, Matt saved time, but he traded certainty for a best-case scenario. He chose to manage a risk he couldn't see instead of choosing the path that would have eliminated that risk entirely. So, where does this leave us? The bracket is installed, the car is running. I'm not saying the engine is doomed, I'm saying it's vulnerable. If Matt is going to drive this car at full power, he needs a protocol. First, he needs a long-term run-in period, not just one drive, but weeks of gradual load increases, allowing the metal to experience heat cycles without being hammered by 1,500 powers. Second, he needs regular microscopic inspection of those weld boundaries. If a crack initiates in that heat-affected zone, it will be visible before it propagates to failure. Finally, he needs to monitor the sensor data logging. Any variance in the signal could be the early warning sign that the bracket is flexing. If he ignores these, he's gambling with the entire rebuild. The bracket decision doesn't define the success of this project, but it does define the difference between a car that looks good on camera and a car that is truly, reliably engineered for the road. The true right to repair is about building things that last as long as the original or better. I hope that bracket holds. I hope in a year we're all looking at this video and saying I was wrong. But until this Bugatti completes a series of full power runs without an issue, the question remains, was the risk worth it? I'd love to hear from those of you who have worked with welded aluminum in high vibration applications. Am I being too cautious, or is the heat affected zone the silent killer in this build? Let's talk in the comments, and subscribe, because when this car eventually hits the track for its first real test, we'll be here to see if the engineering holds.